Hi, everybody. Thank you, Greg, and thanks again, Nina, for putting together this great show, and everybody who helped, especially Shelly and PD. Big shout out to PD. Thanks for all the help yesterday and today. So, I like to start out with this image because my background's in music, actually, and in particular the piano. I grew up playing the piano. And I think that that instrument, more than anything else, has sort of informed, or at least laid the groundwork for how I think about a lot of different things. And I like this image just because it sort of captures what I'm trying to explore in my artwork. The difference between the physical world, this like heavy object, the piano, specifically designed to make noise when you like work with it, when you touch it. On the one hand, and on the other hand, a raw speaker cone like the ones that I used in my piece last night, which is kind of, it represents this abstract world of electronics, the abstract world of computation, and how electronics kind of interface with the real world through things like speakers, speakers being very, very simple objects that translate electricity into motion. And so, before talking too much about anything, I actually want to play you some music from a piece called One Bit Symphony. And this is how it was released as a CD case with an electronic circuit inside, a small microchip in the center. The mouse is really small on the screen. That synthesizes the music you hear when you plug your headphones into the side of the case and flick it on. And the music is all one bit. The one bit in the title refers to the amount of information at any moment in time in the sound wave, either a 1 or a 0, this one-bit binary foundation of information that we know about from, computation, digital information, ones and zeros, this true, false, binary information. And so all the music that you hear is essentially these ones and zeros, these on and off pulses of electricity that are output by this chip, routed through wires to your headphones and essentially translated directly into sound. So it sounds a little bit like this. Oops, that's the wrong one. Here we go. So you get the idea. It's this very sort of primitive, raw electronic sound. And it's a sound I fell in love with when I started working with it, but it took me a very long time to start working with electronics in my formal work, my music and my art. And I think that's because growing up composing for acoustic instruments, this contemporary classical tradition, made me really appreciate the physicality of sound, the physicality of these instruments, and how when someone plays a violin and they run the bow across the string, and the hairs of the bow have a little grit to them, and that grit catches the string and sets it into this mechanical vibration, and because the string is taut, it vibrates at an audible pitch, and that vibrating string, the pitch of it gets amplified by this body and it transmits outwards and it eventually reaches your ears and you hear that as the sound of the violin. And there's so much material involved in that sound. It's such a, that sound is such a product of the laws of physics and the proximity of that instrument within a physical space. You know, the air between the instrument and the listener is important. And that tactile quality of acoustic instruments was something that I had a lot of trouble letting go of. The piano it's almost like it's strangely kind of like a digital instrument, but a physical analog of it, that you have one pitch for every, one string, or at least one string for every pitch, and they're strung tightly into this body that is, you need an actual metal framework in the piano to support so much tension in the strings that the piano ends up being this very, very heavy object, and that's required in order to support all of this sort of physical framework set up to create the sound where when you press a lever down, when you press a note down, a hammer moves up and hits a pitch and you hear sound. So it's this, again, incredibly physical, heavy object that is purely intended for the creation of piano sound. And the identity of that sound is grounded in this instrument, really. The piano sounds like a piano because it is a piano. It's like this one-to-one relationship. And a flute sounds like a flute because you have air vibrating in a metallic cavity at a certain, in a certain shape, in a certain volume, and that creates a resonant pitch that sounds like a flute. And in contrast, electronic sound is more abstract. It's not really grounded in the physical world. The sort of promise, the great promise and wonderful, the consequence of working with electronics and sound was that you could make any possible sound you could ever imagine, and all the sounds you can't even imagine you can make with electronic synthesis, because it's not grounded in the physical world. You can create any waveform. And that promise of the infinite potential of electronic sound, it's kind of this beautiful thing, and I love electronic music, but it doesn't have this this sort of tactile quality that I really love. Like the fact that when I knock on this, we kind of have this very intuitive understanding of what's happening, and you hear this material and the sound of my hand against it, and you hear that as sound. And so I stayed away from electronics in my composed work for quite some time until I was lucky enough to start working with these microcontrollers, these small chips that have come up a few times today at the center of this project and the center of a lot of my work right now. These extremely basic computers. They are computers, they have a little bit of RAM, and they execute instructions that are programmed onto their memory. And the difference between these chips and working, say, with our traditional sense of a computer, this laptop here with a screen and a video out and audio out and USB ports and a keyboard and a trackpad, these chips don't have any of that built in. We take this for granted when we think about computation, when we think about software and computers. Our experience is all about this interface, or this interface. And at the core of all of this is a processor, is this machine that's specifically designed to execute very, very simple instructions. And working with these kind of really opened up my mind, because all of a sudden I was working with computation on a physical level. The fact that they don't have any ports or input and output that you can readily work with means you have to wire everything up by scratch. If you want to communicate with this chip in any way to understand what it's processing, you have to wire it to an output, whether that's a light or a motor or a speaker or whatever. You have to explicitly, physically make that connection. Because computation is ultimately something that is physical. Again, we think of it as something abstract, like in mathematics, math is this beautiful abstract thing, right, that kind of like gets represented by equations on a piece of paper, but math itself is kind of pure, out there, separate from the physical world. And in a way, computation is also, except that the whole point of computation is that it's actually computed in the physical world using the laws of physics. And if you have information that's running on that chip, in order to access it, you have to connect it to something. And the same thing with inputs. If you want to control that chip, you have to wire inputs to it. And so this like very physical side of working with code was really important to me, basically, because these chips are only capable of writing ones and zeros. We already know that ones and zeros are the basis of information. Like when you store an image on your computer, it's stored as ones and zeros. When you access something over the internet, you're transmitting ones and zeros. But we're very rarely in touch with that actual physical information. And again, these chips make that explicit. So these inputs and outputs, read and write, ones and zeros. But, and I'm sorry, I kind of end up going down these like really heady lanes. I'll try to keep coming back to art. And if you have any questions, by the way, just interject, raise your hand. I'm happy to like weave them into the conversation. But these ones and zeros, like a 1 and a 0, again, that's a mathematical idea. They're numerals. They represent the numbers 1 and 0, like a line and a circle on a piece of paper is a 1 and a 0. But clearly computers don't write ones and zeros by default, at least. And so the way information is stored on a computer is in electric voltage potentials. You have a 1 being the presence of an electric voltage and a 0 being essentially the absence. And so those ones and zeros in like software are sort of a linguistic thing, but in hardware are actual physical quantities of energy, we could say. And those ones and zeros, when they're output, these on and off pulses of electricity, can be connected to something, let's say a motor. And the crazy thing is, and this is the basis of computation, is that a 1, this electric voltage potential, we might remember from physics that like potential energy has the ability to do work. And so if I hold something up high and like there's potential energy stored in this object, and if there was a water wheel kind of thing, I could use water as an analogy too, but anyway, this thing would move down and it could turn the wheel and that would create electricity. So that potential energy has the ability to do work, we say. And the same thing is true of the electricity coming out of these chips. These ones and zeros have to have the ability to do work. And so a 1, when you connect it to a speaker, activates the electromagnet in the speaker, pulls the speaker membrane back, and physically moves it, deforms that membrane. And when you set it back to a 0, it springs back into its start place. And so you go 1 0 1 0 1 0 1 0, and if you do that, let's say 440 times per second, you get a 440 hertz tone, which happens to be an A. And so there's this very kind of basic connection between sound, at least in this kind of context, and computation. Does that make sense? This kind of, like, there aren't too many layers there. And one thing that really drew me to the 1-bit kind of whole project is that I was really interested in removing layers and simplifying the system as much as possible. And so that when you have, for instance, like a CD player and it's playing back 16-bit audio, this is like much higher quality than 1-bit. It means that the sound wave of a CD, and I promise I'll show you some more stuff soon. The sound wave of the CD at any moment in time is represented by some value. So it goes from like 0 up, and then back down to 0. And that value is a 16-bit value. So you have 16 ones and zeros, making up this like value at any moment in time. And if you have 16 ones and zeros, and there are 2 to the 16th possible values, so it's around 65,363, I don't remember, a lot of possibilities that you can vary. So if you think about dividing a waveform going from here to here into 65,000 possible values, you can have a very smooth waveform. It's not very pixelated, for instance. And that's why CDs sound pretty good, and DVDs sound even better with their 24-bit sound. And then you kind of think about like Game Boy music, which was 8-bit, early Nintendo games, and their 8-bit sound that has a certain character. It's this 8-bit sound. You only have 2 to the 8th possibilities, which is 256. So you kind of like, you zoom in on that sound wave and you start to see it's a little stair-steppy, and that's part of the quality of that sound. And anyway, all that's to say that like, in order to do that higher bitrate stuff, you need extra parts. You need these digital analog converters. And in general, most circuits have a lot of parts, let's say. And I wanted to just kind of remove as much of that as possible to present this sort of transparent thing. Anyway, I'll move on. So the electronics that I was working with that like led into this album, I decided to actually bring them back into my classical music. And classical music's a weird word, but I kind of like it. By essentially putting speakers connected to these 1-bit circuits on stage with these musicians, playing their physical acoustic instruments. And I was kind of interested in how electronic sound needs a speaker to be realized. And so it's electronic until it gets to the speaker, and then it's just as physical as any other instrument. Like actually speakers, when you look at them, you realize they're basically the same as like a drum, like a tom or kick drum or something. It's like a membrane, on a circular membrane that's taut, and where on a drum you hit it with a stick and it deforms and it moves, right? And you hear that as the sound of the drum. A speaker is like exactly the same, except that instead of having to hit it, you can kind of like sneakily control it and tell it to obey whatever motion you want, and that's the sound you hear. But at the end of the day, they're just like these very primitive objects using super primitive technology. Like it's just a magnet, an electromagnet, that's been around for a long time. So, so these pieces were to explore this kind of intersection between this acoustic physical sound and this acoustic physical electronic sound in the same space. And I did a bunch of them. This one's for harpsichord and electronics, which we almost did here actually, but ended up doing the percussion piece instead. For string quartet and electronics, accordions with 5 speakers, cello. For instance, this is a percussion piece that we just did a couple days ago over in Indianapolis. And in each of these, I'm trying to like think about the physics of the instrument, like what happens when you hit a bar of metal in a vibraphone and it resonates and you hear this beautiful clear sound, versus like the 1-bit sound, this very primitive thing, right? Like, is there any kind of relationship there? And I'll play you a little bit of a piece for 10 violins and 10 speakers. It's called Active Field. And actually, we're just in the process of recording it right now. So I'll just play you a couple minutes from this. The beginning is just strings, then it's just electronics, then they come together at the end, so you know what you're hearing. And so, actually, what happens at the end there is everybody sort of settles into this final chord, this 20-part chord, the 10 violins, the 10 speakers, and they just hold that for 2-3 minutes or so until the piece just abruptly ends. And it taught me something really unusual, which is that these string instruments, these violinists, really good violinists, who've spent their whole lives, learning to play this instrument so well, and this instrument that's been developed for hundreds of years, you can't quite tell the difference between the sound from the violins at the end and the sound from the electronics. And this one-bit sound, by the way, is like the most primitive digital sound you can have. It's the sound that like microwave beeping is usually made of, or like your digital watch in the past. None of us have these things anymore, but it's just like, it's really raw, it's very primitive sound. And so for those two kinds of sound, this extremely cultivated string sound and electronics to be indistinguishable was kind of like really unusual, and I think that is something I've been trying to explore in a lot of these different pieces. Yeah.
The first piece that you played on the CD sounded very much like a Philip Glass composition.
Mm-hmm.
Is that because of the nature of the parameters of working from the one bit, or is that something that's just your kind of what you like to compose?
A little bit of both. My music, I've always been interested in minimalism in general, repeating structures. I think that ties into my background in math and everything. I'm just like intersecting patterns and stuff like that I love. I can listen to all the time, and I wrote music that explored those ideas in general. But also the technology, and in particular looking at really simple systems, like simple physical circuits, and then also simplicity in code, leads itself to certain kinds of structures. And in all of my music, it's actually all through composed. It's all like the analogy of notes on paper, right? So every musical event has kind of like been created by me. There are no generative processes generating music algorithmically. They're algorithmic processes realizing the music that I've written, but not in the actual writing of the music. And so there's this encoding kind of stage and how to represent music, the music I've written for this framework in code, and things like repeating units, repeating cells of notes are very easy to represent in code, and music that's based on some sort of foundational grid of time is also very easy to represent in code. And so since I've been working with electronics, my music has gone more and more in that direction, actually, of like writing music that has a very kind of elegant implementation as like sequences of numbers on a grid. So that's basically just to say that, yeah, the code sort of has lent itself to working with certain kind of music.
So if I may, one bit means you can only play one sound at a time.
It's more complicated than that. No, I often do work with one sound at a time. So in these pieces, I specifically have just one. I usually have one pitch coming from one speaker. So you're really hearing a speaker just oscillating at a set frequency at any moment in time, and those distributed in space, creating polyphony. And the piece I performed last night, same thing. But you can intersect these waveforms to get polyphony. It's kind of complicated to explain, because normally when you mix two sound waves together on a mixer in software or in air, their waveforms sum. So if you have a 16-bit wave and another 16-bit wave, then you have a 17-bit result, right? I don't think it's there. Yeah. And so there's not enough space, basically, for me to combine the two one-bit waveforms and get a one-bit result that way. And so I use logical operations on them, and I have to, like, if I want polyphony, I have to write very, very specific kinds of music, which I do in One Bit Symphony, for instance, and try to explore that. And that actually becomes a character of the one-bit sound. on one hand, it's extremely limited. Like it wouldn't really make, you can't really use one-bit sound to emulate, for instance, a classical instrument or someone's voice or something. There's just not enough information there to accurately. It's kind of it's interesting, but there's no practical, let's say, application of that. So to me, it actually becomes its own instrument. Becomes like its limitations become its characteristics, and we don't think about, for instance, like a violin not being able to play the latest Miley Cyrus song or something. We think about a violin as a violin, this like beautiful thing that has this great character. But a violin's identity, characteristic sound comes from the fact that it can't do everything. It's very specifically wed to its object. Big piano piece, Crotales piece, and so ultimately this brings us to visual art. Because I was exploring this one-bit sound, thinking about information, thinking about computation, and in particular processes, because any code executes process. You have to explicitly generate software as a series of instructions that a computer executes. And actually, thinking about how the software informs the music and vice versa, I started thinking about the processes within a piece of music also as related to computation, let's say. And so it ended up leading to working with this drawing machine that I've built and which is upstairs, as a way of exploring drawing as a process that could be, I guess, sort of coded or encoded the same way as a piece of music would be, as far as like me writing a score as a piece of music and handing that to musicians to perform. It's a little bit like that in these drawings, where I set up a system, set up a visual composition, and I have the machine execute that, essentially perform those instructions to realize this drawing in physical space. And it really came out of thinking about drawing as this basic question of how do you fill a two-dimensional surface with a one-dimensional line? And to me, that was the definition of drawing, at least as far as what I was interested in. This like very stark thing, which is like, how many dimensions does it have? Like, how many dimensions does the mark have? And like, go. And so actually, this is quite relevant in the context of the Mandelbrot exhibition, and Nina and I have talked about this stuff a bunch, that there are certain mathematical ideas like space-filling curves that I was really inspired by, which are mathematical functions which are impractical. They take an infinite amount of information or time to run, but they touch every single irrational point in a two-dimensional surface. But it's a function of a one-dimensional variable, so it's this whole idea of translating a one-dimensional amount of information into a complete covering of a two-dimensional surface. And so I was thinking about that, and I was also thinking about randomness. And Mandelbrot also explored randomness, so these random walks in his work. And ultimately, the drawing machine essentially executes drawings that are these visual compositions of randomness and order, this play between randomness and order, as these basic processes that kind of like also speak about the limitations of computation in general, because we know that computers cannot generate pure randomness. It's a closed system. You can't get like information out of this closed system. But you can get this pseudo-randomness. And so these drawings are kind of just about exploring these ideas visually and composing them into these visual pieces. I'm not talking about this very well. I hope this is making some sense. But so basically, I imagine everybody has seen it upstairs in the exhibition, but it's two motors that connect down to a pen, like this one, which is suspended against the vertical surface, and it's either paper or a wall, like we have in the exhibition. And there's 3 smaller paper drawings that are made the same way. And then the motors essentially have one of two movements each. So there's sort of just four possible movements. And using that system, I wrote some software that runs on a chip, much like the ones in my music, and it controls the path of the pen to slowly flesh out this two-dimensional surface with randomness and order. And in this, the same as in the music, the code is really only half of the system. The drawings don't exist as just products of code, because ultimately the code is moving a pen, and the pen is what's making the mark on the surface. And so the code only goes so far. Again, the code ends at the motors. And what happens in these drawings is that they sort of amplify these natural processes that are part of that system, like the fact that when the pen moves, it's kind of jittery, and the line, the string that's connecting down to it sends these waves in it, and so it's this imperfect representation of what the code is telling it to do. And then the surface of the drawing surface might be textured like the wall is upstairs. So when I do wall pieces, and that's what it looks like right now, or as a half hour ago at least. When I do drawings on walls, I use thicker markers, and over time they run out of ink, and the line gets lighter, but also the tip gets more blunt. And so there's this kind of, all this physical qualities that come from the fact that the pen is making marks in the physical world. And that's like the second half of the drawings, if the first half is the code. And there are these open-ended processes, these kind of, like the core of the drawing software, which is also very simple, is just an infinite loop, which is this idea of stepping in one direction and then deciding whether or not to change direction. And that's like the basis of how the drawings are made, and that runs indefinitely. And the drawing is over either after a certain amount of time or when I feel like the drawing is ready. So this kind of gives you a sense, for instance, of the difference between random motion and ordered motion. And the ordered motion actually is the exact same thing as the random motion, except that the probability of changing direction is 0. So it's actually doing the exact same thing, it just never realizes itself the same way. This is a very, very small drawing, just a couple inches across. And the edges you see are quite spackled and deckled and whatever. That's because the pen is always kind of like moving around. And if I have the motors turning quickly, then the pen is going to jump around more, and it transitions from being a line into like a bunch of specks that slowly build up over time. And the waviness of this one is because the pen kind of like wiggles back and forth as it goes down. So over the years, I've just been exploring these various like consequences of working with the same exact system. And so this kind of led also to thinking about other visual forms, like video, doing these 1-bit video pieces, because these old cathode ray tubes are beautiful devices. They're also very primitive. They're a little bit like speakers in the sense that you send them voltage and they stream electrons from the back of the cathode ray tube to the screen, and they hit the screen and they emit light, visible light. So there's this very direct connection again between like the medium, in this case image, and the sort of mechanism for how that's generated. And it's totally different from these digital projectors or the screens in our phones and our computers, which have so many layers and abstraction of that process that you're not really working with an image as a physical thing anymore. And so I did some installations, and I actually ended up using these televisions in a dance piece I choreographed, because I was thinking about musicians with speakers, and that kind of led to thinking about dancers with televisions, and how speakers and instruments have this sort of like forward facingness. They generally project sound in a direction, and they have this visual sort of face to them too. And televisions have the same thing, and humans also have the same thing in general. And so I did this dance piece that had people moving these televisions around, and I'd cut the power cords and put batteries inside, so they became these sort of building blocks that that they could move around. And I don't have too much time, so I'm not going to play a video of that. And so a few years ago, I started, I don't know how all these things exactly connect. I think it was thinking about one-bit sound and electronic sound in more abstractly than as just music. And it led to doing these speaker installations. These small ones were called interval studies. And they're aluminum panels with this grid of speakers on them. These are each like little speakers. And in these pieces, each speaker emits a specific frequency, a specific pitch. And they're all tuned to span a certain range of pitches. So like this one on the right takes a perfect fifth, and it divides it into 99 individual frequencies. So it divides the fifth on like a piano into 99 pitches, and each one gets a speaker. And so when you walk in and you hear this panel, you hear all these collective pitches at the same time, and then as you move in closer, you can sort of navigate the frequency spectrum physically by moving around the piece. And this piece on the left divides a minor second into 49 pieces. It's sort of the smallest Western interval that we have, like just between a white and a black key on a piano, and just dissects that into 49 individual pitches. And ultimately, these studies led towards creating a much, much larger piece called Microtonal Wall. And then this is a photo from its installation that just came down at MoMA in New York. And it's 1,500 speakers. Same idea, each one playing a specific pitch. And the range is much wider. It covers 4 octaves. From the lower left corner to the upper right corner. And so the result of that is when you walk in and you hear all 1,500 pitches at the exact same time, it sounds a lot like white noise. And that's because white noise is the sum of all audible frequencies. It's like white light, the sum of all colors. White noise is the sum of all frequencies. And when you walk in, you get these 1,500 frequencies at the same time, and it sounds a lot like white noise. And as you get closer to the piece, you kind of zoom in on the frequency spectrum until you can put your ear up to an individual speaker and hear its pitch as contribution to this massive sound. And I'll just play you a little bit of a walkthrough of this. And I wanted to play it as audio. Media, audio, artwork, microtonal wall. Let's do this one. So this is me moving a set of microphones around the piece and sort of like playing it. So there's some other things to talk about, but maybe I'll just step back for a second. So in all these pieces, I guess the fundamental thing that I'm interested in is this connection between this abstract world of computation I've been talking about and the physical world. And I've been programming the last few years in assembly language, and that has, again, had this like profound influence on how I've thought about code and how I think about also the machines that we use in our daily lives. Because assembly is the machine language that the processor actually executes. So if you write software in C or in like some higher level language like JavaScript or something, you're kind of working in these high level objects like if statements or loops, or you can execute complex mathematical equations, etc. And those get translated down to machine code. And what the machine is actually executing is these very, very, very simple steps that essentially in combination execute the software. Like for instance, the software that's running on this computer right now. But working in assembly, it really makes you feel like you're working with a machine, like almost something mechanical, because an instruction in assembly might be 16 bits long, for instance, or 32 bits long, and you get the sense that these bits, these ones and zeros of the instruction, get fed into this processor, the algorithmic processing unit of a microprocessor, and the first few kind of tell the processor what instruction is getting executed, and those might be different length depending on like how the processor is going to work with the information you're giving it. And then the next few might be some variable you're working with, and then maybe a number or an offset in memory or something. And the processor is specifically designed to take these physical ones and zeros and kind of like do computation with them, like cascading on top of the laws of physics to take this instruction, this line of code, and actually execute it physically. And when I started working with computation that way, we know a computer is not made out of like gears or anything, but it almost feels that way. It makes it feel like something very, very primitive that we can understand. And I think that is something that's very important right now, is understanding the technology that's around us. And something I guess I'm trying to comment a little bit on through this work is that we place so much trust in all of the media and technology that we use around us, yet we are so disconnected from it on a fundamental level, the sort of level of information and process. And especially with web services, or when you buy a device that may or may not have access to the microphone anytime it wants, et cetera, et cetera. Like, we place so much trust in these systems that other people have built. I don't exactly know where I was going with that. It's something that's been kind of really meaningful, I think, right now especially, and in terms of like where a lot of my thinking about my work comes from. Because ultimately, like there's something strange about the limits of technology, the limits of computation, which is that like the limits of computation are not about how high quality of a film, like the next Pixar film, is going to be, like how photorealistic that animation is going to be, or how good like Siri is going to be at understanding your questions. The limits of computation are actually much, much lower level, and they were explored back in the 30s, for instance, by Alan Turing and Kurt Gödel. Like a time, I'm actually really inspired by the early 20th century when we were really interested in exploring the foundations of the world around us, both the world of physics, for instance, with quantum mechanics, finding out the building blocks of the universe, as well as the foundations of computation. And it turns out that the limits of computation are these kind of universal things, like the fact that computers can't generate randomness, or the fact that there are certain things that are not not computable. Like, for instance, it's impossible to know if a given computer program is going to run forever or not, which seem like very, very sort of strange, simple questions. But those are the fundamental limits of computation. And those are the things actually I find really to be the most inspiring. And so somehow that all weaves back into what I'm talking about. I'll leave that up to you guys. But yeah, maybe that's all I have to say about my work. I'm totally happy to take any questions if you have them, though. So thanks.